Okay, so we start the last discussion by summarizing quickly what has been said, and I'll try to highlight what I find the relevant points and the common theme that emerged from the presentation. So, first of all, let me say I appreciate a lot the original question, the starting point, which is, I think, based on the idea that comparing, contrasting, even violently, and then also merging different quantum gravity formalism is the most efficient way of solving open issues and obtaining the full picture. And in fact, I repeat, this is exactly because, as Carlo said in his presentation, we have learned a lot from several formalisms, in several corners. So when people say, we are missing that, we're missing that ingredient, there is this or that open issue, we don't have the full theory, that should not be misunderstood as meaning that we know nothing. We have learned a lot of things, and it's good to compare and merge. And Laurent has mentioned several corners where we can get insights from, particle physics, ADS CFT, and loop quantum gravity, quantum information, and so on. And he has mentioned a few ingredients seen from these various corners. My impression is that all the presentations in the previous session have basically shown that there is one common theme, and now, I mean, pessimistically, that may have to do with the fact that there was some pre-selection and people in this room already agree on a number of things, and that means that we have to struggle a little bit more to look beyond what we already agree on, and we have to try to reach out to people and corners of the quantum gravity research that are farther away to really get new insights. Optimistically, it may mean that we have actually found a common theme that we can build on, and that is the idea that boundaries and subsystems and their relations have priority. Before I expand on that by recapitulating what has been said by Carlo, Laurent, and Wolfgang and the other speakers, and all of them, let me point out that Laurent showed this picture of the elephant, and some people in the room may not agree with some underlying assumption there, which is that there exists an elephant out there and we just have to find out the full thing. But I would say that exactly the same story goes through if you believe in a more participatory construction of reality. It's still the point that you have to merge, connect different perspectives, each partial. Anyway, boundaries and subsystems and their relations. Well, something we've learned, according to Carlo, and I would agree there, is that space is only has meaning in relative terms, as a relational construction. The same is true for localization. And the extra ingredient is to realize that geometry has to be dynamical, has to be a physical entity in itself. And dynamics, from this point of view, has to be found in correlations. This leads to the idea of focusing on space-time boundaries. And then there is an extra point that connects to all the work on foundations of quantum mechanics, which is that one can at least tentatively identify this space-time boundary with the Heisenberg cut. And so there is at least a parallel, take it just an analogy to start with, between this chopping space-time in blocks, and so separating a given local space-time region from the rest, with the separation between the system we are interested in quantum mechanics and the observer, the context that allow us to define it. So that sometimes this can be rephrased as saying that the space-time boundary can be identified also with an epistemic boundary, with the epistemic boundary. Then we can discuss on the epistemic terms. If that is true, and also from more general arguments, one could suggest, and it has been suggested in the third talk, that general boundary formalism is the most general and appropriate language for quantum theory and for quantum gravity as well. And in particular, it's a very convenient framework to analyze space-time localized measurements. And the argument was you can also use it very efficiently to understand causal structure and fitting very well in an operational perspective on physics. And then we will meet the issue again in the, later on. Is also a good framework for giving meaning to probabilities in this space-time boundary context, which is a key issue and will be a key issue for quantum gravity in general. The boundaries, the focus on boundaries is the endpoint of any journey that tries to ask what are the fundamental degrees of freedom of quantum gravity. That was the other conclusion or claim or suggestion that I take from Laurent's talk. And similarly, the related question of what are the fundamental symmetries of quantum gravity. The key suggestion, in fact, is that the way to identify the fundamental degrees of freedom and the fundamental symmetries, what we have to do is exactly decomposing a gravitational system into subsystems, if you want space-time into local regions and space into local regions. And that leads also to identify entanglement as the key element for gluing together subregions. Then a more concrete proposal is that of local holography as a way in which indeed we can merge together the insights from a number of quantum gravity formalisms. And that more technical are the boundary charges that we find in a local region that correspond or at least point to the fundamental degrees of freedom in quantum gravity. With the boundary symmetries corresponding to such charges used both to identify the relevant quantum geometry and for a description in terms of a fluid-like continuum picture. The other point that was not mentioned, but I think is directly related to what has been said in other talks, also during the other sessions of this conference, is the fact that the same boundary degrees of freedom can be understood as providing a reference frame, and that fits very well with all that has been said before. Then Wolfgang reminded us that a very convenient and effective strategy is to go discrete. And there you can also implement the same insights and suggestions that have been pointed out by the other speakers. He reminded us of the Regge picture of a space-time discretized into local cells which are then glued together, and reminded us that spin networks and spin foams that are cornerstones of a number of approaches and formalisms for quantum gravity, and in particular, of course, loop quantum gravity, are just the quantum version of that idea, or at least they can be seen as the quantum version of that idea. So that you have at the dynamical level, local quantum amplitudes for discrete space-time regions glued together, and spin networks are the boundary states. And probably a good starting point for the discussion is the last part of Wolfgang's talk, in which he immediately he suggested a number of key issues that arise in this context. Probabilities, that has been already mentioned. What are probabilities without a preferred temporal or causal structure? And what is the generalized Born rule? And can we avoid any use of unitarity in defining probabilities and quantum mechanics? because in absence of a preferred time and causal structure, it's not obvious what role unitarity could play. And then he mentioned symmetry, charges, and observables, which also had to be found relationally and at the boundary. And then he also reminded us of something that we always forget, which is that in such a picture, just as in fluid dynamics, dissipation of some form is inevitable, and we have to take into account in our quantum gravity models. Well, that's the material for the discussion. Now it's up to you. I will direct. Lucien?
Hi. On this point about probabilities, the generalized Born rule, if you consider, so if you're trying to calculate a probability, like the probability of A given B, that only makes sense if B provides sufficient conditioning that you can have a probability. So there are many, in fact, generically, if you take two propositions and ask for the probability of A given B, you won't have sufficient conditioning. Like the probability that Donald Trump will be the next president, given that I drop this, is a meaningless statement. So you can't. So when this paper I wrote on causaloid approach, so in the context of quantum gravity, it becomes that issue becomes more important, because normally the way that we choose statements A and B so that there is a well-conditioned probability is causally. We make it so that B has a certain causal relationship with A, and that's how the probability comes to be something that is well conditioned. But in the context of quantum gravity, if you have indefinite causal structure, you may not always be able to help yourself to that situation. So a number of years ago, I proposed a way to deal with that, which is where you have a two-stage calculation. The first step in the calculation is to see if there is a well-defined probability. And then if there is, the second step in the calculation is to evaluate that probability. And it seems to me that something like this might be essential in a theory of quantum gravity.
Is it fingers first, comments or follow-ups to the previous comment? Is that a comment?
Maybe just a comment. Yeah, comment. Just super short. This is a key question, but isn't this exactly the question that was addressed? Okay. Yeah. No, this seemed to be the key question, which becomes a very practical question when computing things. But isn't this exactly the question that was addressed by the man in the talk? Isn't that the question that the positive formalism, the boundary formalism, are trying to address and make it precise and give a precise answer to that? I guess the question is to both of you, Lucien. Is that the question you're referring to?
So I mean, I've spoken to Robert about this, and he didn't agree there. I think the formula they have is to calculate a probability under the assumption, and the assumption is that it's well conditioned. But maybe Adam and Martina can talk to that now, because the thinking may have evolved.
Good afternoon. I would like to mention something that it hasn't been considered in the topics and in the approach that we have been touching in this conference, because maybe there is something that we are missing in our approach to quantum gravity. It's not my idea, to be honest. It's the idea of someone else, but I think that it's important to consider it because we are not taking into account. Maybe the geometry that we assign to our physical world could depend on the object that we use to define it. To be a little more precise, Well, let's remember to general relativity. In general relativity, space-time is considered a four-dimensional manifold with a Lorentzian metric. And the Lorentzian metric has two roles in quantum in general relativity. In one hand, it's the dynamical part of the theory, but on the other hand, codifies relations between the matter constituents of the theory. The metric codifies information about geodesics, which are the trajectories of the particles in the theory, and we define events as intersection points between geodesics, and we can measure the distance between two events and things like that. So in that sense, the geometry is in some way depending on the way in which we are defining it, in the matter constituents of the theory. So, for example, if we try to quantize the space-time metric in some way, we will obtain an object, a quantum object, but which carries information about classical constituents. So it will be a strange mix because we are quantizing one aspect of the metric and not the other. So maybe, special relativity was constructed. We needed to abandon the idea that the fact that two events are simultaneous is an absolute fact. We need to consider that if two events are simultaneous, that depends on the observers. The proposal of relational quantum mechanics is that maybe we need to abandon the notion that the state of a system is independent of the observer. Maybe it could be important to consider that the way in which we assign geometry to our physical world depends on the matter constituents that we are considering. If we try to describe the quantum nature of the gravitational field, well, we cannot define geometry using the standard object that we used to do so, because particles are not anymore part of the realm of the physics that we are trying to describe. So it's a perspective that hasn't been considered in the approaches that we are taking here, that we are speaking here in the meeting. So I think it is important. It could shed new light into some aspects, and it is important to consider different ways to attack the problem. But this perspective, I don't know why anybody takes into account this point of view, but it's important to consider different perspectives of the problem, especially this one, because it's not forgotten. I don't know why, but I think it's important to take into it.
Okay, thank you. Is there a follow-up comment on that?
Yes, so I think it's a question similar to yours, perhaps a complementary one. So I think that in the first and the last talk, you insist a lot on the ability to choose arbitrarily shaped boundary regions. So first of all, I'm a bit, I would like to know how arbitrary they are. I mean, I guess they are a bit convex shaped. Also, you insist on the fact that there's no input and output, and I agree that you could decide that the input is the output and the output is the input, but maybe from the classical geometry that's around, we can still know how light goes through. Okay, but still, because you somehow give up on unitarity at some stage, you need to renormalize. You need to consider that this is an open system, as the last talk was really emphasizing. And the way you renormalize depends a lot on how you chose your boundary. And so suddenly, you wanted to have some theory that was very covariant, that you could choose a boundary in a perfectly arbitrary way, but no, you renormalize in a way that depends on this choice of boundary. And so you're back to something that's non-covariant.
further follow-ups or you? Yeah, Wolfgang.
Hi. Yeah, perhaps I can answer or give my opinion on that. So, how the boundary is organized, whether it is time-like, space-like, what kind of components it has, all of this has to be encoded into the state. So the state describes what physical situation we are trying to describe. For instance, if we want to understand what a black hole evaporation or just a process where something falls into the black hole, then we will choose states that should be peaked, that have some component that have a semi-classical description that describes a geometric null surface. So this is not breaking covariance. This is just, I mean, choosing a point on state space, choosing a solution of the Einstein equations breaks covariance in the sense that we pick a solution, and one solution is not the same as the other one. So yeah, so the choosing different, analyzing the amplitudes for different physical systems amounts to break covariance in that sense. But this is just a way of saying that different spacetimes are not diffeomorphically equivalent. So there is no breaking of diffeomorphisms in that sense.
It's just to add to what Wolfgang is saying, just to help clarify maybe the intuition. So the covariant is that you need to get the same physics for whatever boundary surface you choose. The state will depend on it, and so will the normalization. That's fine. Now, what does same physics means? Well, you need the same probabilities of outcome, and then what are the probabilities and the outcomes? That's more tricky. There is one example that was the black-white, where this has been. There is a concrete example of what is meant by probabilities. I don't actually know the status. I haven't looked at this the past 2 years of showing independence of the boundary surface chosen. Maybe Carlo can comment on that. But that is the idea. Whatever boundary surface you choose, you need to get the same probabilities. And it's crucial that it doesn't matter if you choose it convex and it looks like you have a future and a past one, because you cannot take out the corner. There is this sub-manifold of codimension 2, the sphere that is gluing the two together, where you will also have boundary data. And those you cannot say that they're in the past or in the future.
So, okay, I'm fine with that. So now you define, you have a problem, you define a boundary, and you say, in a sense, okay, the problem I want to resolve defines the boundary, and inside my theory is covariance. But then that means that you cannot compose these diamond-shaped pieces of regions. So what you lose then is compositionality. That is, you cannot say, here is a big boundary, let me break it into small boundaries arbitrarily. Because for each guy inside, you need to renormalize the thing, or you need to, yeah. So I think you lose compositionality then.
I don't, I don't think you lose composition. And the way to seeing that is make a small model where the same happen, which is to do a one-dimensional case in which you have one-dimensional system and treat it covariantly, which are an example with all these models that for a very long time were studied as models of the general structure of the theory to understand how covariant dynamics could be formulated. And this was, it's a model that was done in 25 different ways for long. And you take, say, a one-dimensional system and you promote the t variable as an independent variable. So you introduce a parameter tau, and you have the your variables x as a function of tau and t as a function of tau, but the action it's written as an integral in the tau, and the action is general covariant at the change of tau. So you've done something apparently stupid. It's the only interest is that now you have something that looks like formally the way general relativity is performed. So now you can do a path integral. You can define a path integral in tau, okay, and compute transition amplitude given x0, given x1 and t1 and t1 at some initial tau, the probability of, and write the path integral. And then you see that what happens is exactly what you expect to happen. First of all, the transition amplitude don't depend on tau. Just magically tau drops out. And you say, oh, well, how could it drop out? Of course it drop out, because the action doesn't depend on the choice of them. And also, the functional integral from initial state to intermediate state, integrated over the intermediate state, and then from the intermediate state to the end, give exactly the same result as from intermediate to the final. How is it possible? Well, because the parameter tau just disappear from the equations. And this formally is a projector, so you just do it twice. This is p squared equal p, formally. I mean, then you have infinities and things. So once you do the strict general covariantly, you can do composition, and composition doesn't do anything, because if you're asking the same question, what is the probability of going from A to B, there isn't another parameter in which you can compose.
Yep, Lucian.
One thing to push on is this notion of boundaries between regions. The idea that you, like in the general boundary formulation, you compose regions from boundaries. You compose regions at their boundaries. If you think about that, you think about what a boundary does is it establishes a pairwise relationship between pairs of regions. And if you expand that out, you sort of get a graph. So with the regions represented by nodes, and the links represent where they join at boundaries. And that structure isn't the most general structure. You can consider hypergraphs where you have nodes that are linked by hyperedges, and those things could, in principle, crop up as well. So recent work I've done with Nitika Sakawada, those objects crop up in the context of a general probabilistic theory for looking at indefinite causal structure. And so I'm not sure if that's just a mathematical curiosity or whether it might be physically relevant in a theory of quantum gravity, if the idea of a boundary might actually break down ultimately. It's certainly something that we are free to explore.
Anyone wants to comment or add to what Lucian said? No? Any further? Oh, yeah. Yeah.
Does it need to be a follow-up now, or can I? Okay.
You have no competitor.
Okay, so there are some recurring themes here, and one is the Hamiltonian constraint or other constraints, how we implement them. The other is now this was suggested that somehow this boundaries are important, but there are two types of this kind of statement. One is in the more traditional holographic sense, which concerns spatial holography, whereas in the general boundary approach, it's more like a space-time picture. But and then you said yourself, it appears like this is the best approach, the general boundary approach, if I understood you correctly. So, I mean, I wanted to ask, I mean, that there were a few formalisms that were presented here. Shall we search for other formalisms? Are we all completely satisfied by the existing formalisms that we have available? And in particular, for instance, the boundary approach, I'm very fond of it myself, obviously. At the same time, I intuitively feel that I would like to have a theory which is a little bit more bulky somehow. That does not, because we have all this intuition from classical physics that is, we have intuition about thinking about classical fields, whereas here in this approach, the field, we do not have a quantum picture in the exact same sense. I mean, of course, you can introduce classical fields, use path integrals to obtain the state on the boundary and so forth. But there does not seem to be a suitable kinematic picture to deal simultaneously with the quantum mechanics over space-time in a bulky way. This one, for instance, I feel is
I don't know if I answered the question now, but I think the idea is that, well, in quantum theory is about states or superimposing states, or what would be a classical state otherwise if there is no H bar. And states are not localized in space-time. They represent solutions of the field equations. And solution of the field equations are associated to initial data on a Cauchy surface or on a boundary. So that's why states are localized. That's why states, so they are not localized, but they are belong to a boundary. So that's
true. That makes a lot of sense. Actually, the formalism makes complete sense. I just it was more about the comment.
But then I agree with you on one point. So I do agree. I mean that if you look at quantum theory, it's kind of so it's defined by a Hamiltonian set of operators, Hilbert space, and the Born rule. And if we, but then we have different systems to which quantum theory applies. We can look at hydrogen atom or harmonic oscillator or a free particle. And in that situations, we have perhaps different Hamiltonians or different Hilbert spaces, different operators. But the Born rule is always the Born rule. There's no free parameter to tweak. And this is something that I found always in a way strange. So why is there no, so if in 100 years time there is another theory, I wonder if that's precisely where something new comes in. That, but this is just a complete, I mean, this is just a speculation.
Yeah, I agree with Wolfgang said. I will also react to your sort of a sense of unhappiness. Can we do more somehow? The way you pose the question, and I think it's common. We all share it. But I would react to it sort of making the point that quantum gravity is a quantum mechanical theory. At least the quantum gravity on which some people are working is just a case of quantum. So there are questions about quantum gravity that keep being posed, which are really questions about quantum mechanics, not question about, in particular, the application to gravity. And of course, the question about quantum mechanics is that, Heisenberg came back from Helgoland writing a letter to Pauli saying, and the electrons, I don't understand what's going on, but the electron doesn't have a trajectory anymore. And 100 years later, we don't understand what's going on, but the electron doesn't have a trajectory. So what I'm saying is that if you think about, I don't know, CERN experiments, you throw things in, do a calculation, and then your probability of what comes out. And what happens? We would like to have a picture of what happened in between. And the only picture we have is, I don't know, we do Feynman graphs, for instance, in perturbation theory. So it's happening this, you know, with a certain complex number, and this also this with a certain complex number, and also this, and we have 12 terms, is happening everything at the same time. What the hell is going on? So either we have, so this becomes a problem in quantum theory. Quantum theory doesn't tell us what happened in between, unless we interpret quantum theory as, you know, we give an ontological weight to the wave function. So then what happened in between is a wave function evolving. And you can do that in quantum gravity. Nobody forbids to do that in quantum gravity, but then you have a quantum superposition of universe with different geometries, and that's your ontology, if you're happy with it. But then you have the problem of how to do the measurement problem from that perspective. You know all these things very well. So what I'm saying is that a lot of funny strangeness of quantum gravity seem to me just as the usual strange of quantum mechanics when you use it for describing the gravitational field, having understood that the gravitational field is the thing we use for measuring distances, and it's what we measure when we measure with a rod or the clock. So either we think that quantum gravity is going to tell us something more about quantum mechanics, which I don't think so. That you were saying this morning might be, but that's a different research program. Or we have to live in quantum gravity with the same unhappiness that we have for a single quantum non-relativistic particle.
I just wanted to clarify that my question was more about the mathematics of it, because we speak about frameworks, and I understood that I meant it in the same mathematical representation. So the question seems to me natural is whether there might exist another smarter, clever, or useful alternative representation that is more kind of bulky in essence, rather than the because we do have this problem with when it comes to the time dimension. Over the spatial dimension, we can write down, we can imagine, you know, Hilbert space that's interpreted as configurations or over that, but you don't have that simultaneously over the space-time in the bulk. You always can only have it on the boundaries, and yet intuition kind of makes me want to have that formalism mathematically somehow.
Yeah, so the way you view it is mathematically, each given quantum gravitational problem, I think you can, first of all, this is not a boundary at infinity, right? This is a boundary around a quantum gravitational phenomenon, a black hole exploding or something else. We're describing a process. The inside is a process. Process is a quantum process. The best we can do about the quantum process is the probability that it happens. And then, of course, it's delicate and complicated to compute probability. What do you mean? Normalize. We don't find the right normalization. So. But the process is just determined by its initial and final. And in between, the best picture we have, seems to me, it's Feynman picture, which is we are summing over possible histories. So we're a functional integral of all possible geometry inside or possible matter configurations. And I don't see how we can feel more than a sum of histories. So conceptually, we're just doing what Stephen Hawking told us to do. Quantum gravity is just the integral, given a boundary, given the integral on the geometries and the matter fields and everything in between. Everything can happen in between. And you wait with the exponential of the complex action. And this gives you a probability. And what happened in between, that's the same thing as where is the electron in the hydrogen atom. So we don't know. Or it doesn't mean anything. So, Pierre?
Yeah, it's both maybe a follow-up and also a question more general that can open us up to, or the dimension of the discussion, is that okay, I am a young physicist, and now it's 6 years that I'm trying to understand quantum gravity, that stuff, trying to make sense out of it. And sometimes I'm very enthusiastic about it because there's finally some notions and concepts that I can make sense of it, and that's illuminating.
and I'm happy. But sometimes I'm also disappointed because I realize that I will never be able to catch up with everything and to read all the papers that have been written about quantum gravity since this question has been raised. And there were presentations that have proposed, shown that there were many formalisms to deal with the questions. I feel that we can always come up with new formalisms. I can invent new mathematical thing with new fancy names with Greek origins, and then spend the rest of my life trying to link that new formalism to the things that have already been devised. And maybe I can call this science and be happy with it. But I think also that somehow maybe one of the role of a generation of scientists should be to be able to make a good synthesis of what has really been learned about the things, and not try to make things more complicated, but make things simpler so that the new generation can learn it faster than the generation has produced it. And to this, I'm not sure that the older generation than mine have been completely successful in this, because there's so many formalisms, there are so many things around that it is difficult when one tries to enter the field to get rid of the noise. And I feel that there is a lot of noise, many concepts which are floating around and which are used in a sense or another in a bit like keyword thinking. And so I have two questions. One big question, which is somehow you've presented what were the formalism that existed, but my question is, what do you think needs to be forgotten? What are the things? What are the mistakes that have been done in the past that should not be reproduced by the new generation? And it's not only, I mean, I would be happy to hear all answers to that questions, but it's not only telling me, well, forget string theory, but I would like to know a bit deeper, why is it, if string theory is indeed a bad way to go, why is it that at some point people have made a mistake to go into string theory? And yeah, that's my questions.
So, Al, is it related or? Okay, yeah. Related.
Hi, I'm Erickson from University of Waterloo. I just wanted to continue his comment. I'm a PhD student of, basically I'm 5 years in graduate school, and I feel like the elephant is going to eat me up. So I'm also trying to make sense about all this, and in particular to complement the issues that he mentions about what are the issues in the past that should probably be kind of like forgotten or in some sense. But I also have a feeling that when I learn certain aspects of quantum gravity or fundamental physics, I'm not exactly sure why new formalisms, new approaches come up when I feel like some of the older concepts are not fully understood. For example, even just algebraic quantum field theory, there is just free fields, like there's no interactions, right? I feel like we don't even understand enough entanglement in field theory that as far as I know, until 2021, we only know how to compute relative entropy between two field states. They are like extremely simple. So we don't even really know what relative entropy for most states are, and we are already talking about like a lot of entanglement between two gravitational subregions and a bunch of other much more advanced concepts. So I'm not sure what the community feels about it. What exactly have we really understood versus the stuff that needs to be abandoned, some stuff that needs to be really pushed forward, some of the stuff that we should really keep no matter what happens, and so on. I would like to hear what everyone thinks about it.
So if it is on the same topic, then we have Chaslav, then Wayne, and then Laurent. Same topic, and yeah, and then the first.
It's rather a comment on Pierre's. I think. Thank you, Pierre, for raising this question. It's about sociology, not about physics. But I don't understand fully your concern. You're saying we should not develop formalism because we already have some, or you're saying there is a lot of noise. This is a part of the job. I think the thing that worse could be done by the older generation is to be dogmatic and to suppress the noise. The noise is there, and a part of your role is to extract the signal out of it. And this will go just by your own intuition, what you hear and believe in. You don't need to understand everything. There is too many things. You should not do it. You should hear other people speaking what they have to say, and on the basis of that, make a selection and go forward and develop your own things. So I feel we should not forbid people producing noise, just the opposite. That's the first message. Maybe the second message is, when I was of your age, there was still around this dream of the final theory. And I still hear sometimes people saying we all know everything about fundamental physics. We just don't understand dark matter or dark energy, or depends on your taste. And this so much reminds me on the two clouds on the bright sky of physics at the change from the 19th to the 20th century. And you all know what happened with these two clouds in the dark, or the bright sky of physics. One cloud was Michelson-Morley experiment, and the other, the black body radiation. There is no reason whatsoever to believe that we are in a very special historical moment when the story about fundamental physics is over. Why should it be? We actually cannot even conceive what the next step will be. But even more, we don't even understand what the present status is, judging from the discussion the last couple of days. So that's all.
Wayne?
Oh, I just wanted to make a historical comment. It has always been thus. We can now go to the bookstore and buy a textbook of classical electrodynamics, Jackson, or something like that. We get a nice, clean theory. And a lot of that has its origin in the 19th century. But if you go back to the 19th century, you see noise, booming, buzzing, confusion, that sort of thing. Similarly with the current textbooks of classical mechanics. So these nice, neat textbooks of certain subject matters, the textbooks of classical electrodynamics, as we know them, originate in the 20th century after it had already been clear that classical electrodynamics wasn't right and need to be superseded by a quantum electrodynamics. So I think you're going to get what you want at a future time when quantum gravity has already been superseded by its successor theory.
So this is just a comment from the outsider who's mainly teaching undergrad students. So I sometimes feel when I'm teaching, say, for example, quantum mechanics classes, and most of a modern textbook just basically teach them a formalism. And I can see my students just basically say they're learning, can calculate, but really don't see not just the history, but what is the point of all these. And sometimes some of the textbooks, especially the books, say, written by Weinberg, for example, always have this sort of historical context with the important questions. So what were they asking at the time in that particular context, and what were the solutions at the time? And I think that, in some sense, is a work of some people. And I just want to comment on the fact that I really like the fact that we have philosophers here, because I always felt that they are the ones who actually kind of clarify the questions really sharp. And sometimes I feel it's very helpful to read those sort of kind of outside perspective on the summary of just the questions and what they achieved, like histories and philosophies.
So Francesca should be the last, but sorry, Laurent and then Francesca. Yeah, yeah, go Laurent.
Okay, let me try to address the question of Pierre and the question there. So it's true that, you know, people work in quantum gravity like myself, you know, what you're saying in these 15 minutes is the result of a long journey. And maybe we need a longer session to go there. To answer Pierre, in my presentation, I was trying to be magnanimous. That is, you know, I looked at the previous blind man, and I picked what was good about what they're doing. And I think this is the way forward. Now, I could spend a lot of hours with you explaining you what was not good in what we're doing. So there's a specific filter that you have to apply from the previous theory that move forward. So, and to go back to the question of, so let me give you an example of, you know, why I'm doing what I'm doing right now and what it is the thing to do given everything we know. It goes back to the question of Pablo. Like, you know, I'm one of the founders of spinfoam. I wrote some of the first papers there and I worked in that, but I'm no longer working in it. I'm working with these things. Why? Because of Pablo's question. Pablo's put his finger on exactly what's the key point. The key point is that you want to, you know, construct a theory. So what do you want to do? You know, if you want to answer your question, you want to go beyond algebraic quantum field theory, you want to construct a quantum field theory that expresses the principle of general covariance. That's really what you want to do. Okay. And then for that, okay, you just, instead of thinking that your states on equal time slice, you wiggle them because that's just what the GR does. And then, okay, so you become a bit more flexible into the boundary condition. And then you want to have some kind of atomistic picture, like Carlo talks about the Feynman diagram. But the Feynman diagram, you know, build up something which is unitarily, which is what Pablo is talking about. So let's say you have a decomposition in terms of these fundamental building blocks. That's, let's say, the spinfoam approach. And now, very good. And then you postulate some rules based on whatever is your kinematical Hilbert space you think it is. And if you want, you can replace it, spin network, by something else. And then you build. So as Carlo was saying, well, spin networks are composable. Okay, very fine. But Pablo's intuition was right. They're going to break different invariants. In what way they're going to break different invariants? So and that's the challenge. The challenge is you will be able to construct an amplitude which doesn't break different invariants. What does it mean? It means that suppose you want to go from the state A to the state B. There's many different histories in which you can first, you know, add building blocks on the left, and then on the right, or start with the right, and the middle, and the bottom, and then you end up with the same state on the B. So a diff invariant theory somehow is a theory which is independent on this choice of slicing, right? And Wolfgang was very careful, because he also works on the things that I'm doing for the same reason. He was very careful that when he mentioned spinfoam, he mentioned three-dimensional spinfoam. Why did he mention three-dimensional spinfoam? Because in three-dimensional spinfoam, it works. Okay, and the reason it works, so in three-dimensional spinfoam, this formalism, which is very categorical, exactly satisfies all the axioms you want and does not break the symmetry. But it's something you have to check. It's like, you know, not any rules you do. So, okay. Now, if you try in 40, you know, and we are very happy to construct spinfoam amplitude that look like semi-classical ones, but they fail your property. So, you know, they fail this property of different invariants. That is what you want to construct. So, what are we doing? You're like, you know, you're stepping back. We went a long way, and you're like, oh, wait a minute. So now, you know, I can construct an amplitude, I can construct a spinfoam, but this one is going to be to break the different invariants. And as Pablo is saying, people are saying, well, one way to go, and maybe Daniele can comment on that. There's, okay, maybe I should sum over spin form, or I could renormalize, or I could just, there's different attempts. So this is maybe a debate that took place 8 years ago, and, and people try different things there. And another thing which is happening is maybe to just step back and to realize, well, if somebody comes into the room, the guy that can see the elephant comes and gives you the right spin form amplitude. How would you know it's the right one? What test would you make this object satisfies to convince Pablo, you, that in fact you're done, that this is the right object? And I don't know how I can convince in 2 minutes, but that's exactly what this understanding, to go back to what is a state, what is the property of a state that carries diffeomorphism invariant charges, that carry energy, local momenta, and etc. So whatever you're seeing today, it has, as Daniele was saying, it has to be done. Now, why didn't we do it the first time? Or maybe it looks cumbersome, but, to answer Pierre, because, you want to have your feet on firm ground. That is, you want to be able to have a representation of the theory which carries a quantum version of diffeomorphism invariance. And that can only be seen when you just cut upon your states. It took us a long way to get there. So there's, I think, it goes to Pablo's point here and your point there.
So
and maybe Daniele can comment because,
So Francesca and then Carlo try to be brief, and then we take a break, a short break. We start then from the same point.
I wanted to answer to Pierre, and I don't think what he was asking is a sociological question. It's really a technical one, in a sense. What we do when we do quantum gravity is really about try to do this process of looking at what are the ingredients of two theories. The ingredients. I'm not going to use this. The whole process of doing quantum gravity is exactly this program of looking at what are the basic ingredients of the theory and try to go to the core and get rid of all the other things that are dispensable. And this is the recipe to do the merging of quantum gravity and quantum mechanics. So we wanted to go towards a conceptual parsimony, I would say, even though sometimes going this route is a bit dangerous, in the sense that, for instance, you can go towards a categorification of quantum gravity, describe spin forms using category theory, more in general, or like even in quantum mechanics, of course, you can use sophisticated mathematics, very abstract, much more clean, much more poor to describe the theory, and not necessarily you get conceptual clarity in this way. Very often you want to just to understand physical processes, understand how a black hole evolves, how cosmology, what is the dynamics of our universe. So it may be that you may want to use different frameworks and you want to adapt your theory to that particular problem. I don't think this is a problem. The multiplicity of perspective with which you can address different problems, it's a richness. We don't have to fear it. But I agree with you that deep in your heart you wanted to know what is the conceptual core of the theory, and of course to do so you need the help of philosophers. They are trained to do this kind of job, to get the conceptual clarity. And if I think of what is happening, for instance, for the philosophy of space-time, a discussion about general relativity, there is exactly a discussion about what is dispensable in general relativity. And one example of this comes from the discussion about what is the role of the manifold in general relativity. So the manifold is dispensable, is a thing you can do without. You can define your theory in a purely algebraic way without referring to the continuous manifold, and yet general relativity could be well defined. I see in quantum gravity the spin network state playing a similar role. So the manifold is a tool on which we construct our theory, but the gravitational field is not the manifold. In the same way, we use the spin network states that are wonderful. They are automatically diff-invariant. They have a beauty in coding relations between different systems, between different regions of space. But of course, the gravitational field is not the spin networks. And the spin networks very often introduce a bit of a confusion in the new practitioner of quantum gravity, because there is a discreteness there that is not the quantum discreteness. It's a truncation of degrees of freedom that is introduce a discreteness that is not the quantum one. So you have two discreteness in the theories, and constantly people mix up the two things. So on one hand, you have the genuine quantum discreteness that comes from the symmetries of the theory, and on the other hand, you have the spurious discreteness that comes from the truncation, the use of a lattice, the putting of your field into a box using finite boundaries. So in this sense, okay, so if you ask me just a question, okay, what would be one of the things you wanted to get rid or you wanted to be cautious about in quantum gravity, maybe I would say always be careful with the states that you're using. The network states are beautiful, are my favorite one, but they are not, I don't want to stick with them. I don't want to attach to them the ontology of my theory. For instance, Wolfgang has recently worked out, maybe Eugenio also, that they were coming back to the original loop state. So I think with the spin network, we have learned a lot about the fact that we wanted to describe our theory in terms of these interactions, relations, and so on, but we don't have to attach the ontology of the theory there. So the conceptual framework of the theory is not attached.
So we need to wait after the break.
Really, really brief. Notice that people are already eating.
Well, we can wait after the break.
We can start from the same point after the break. Okay, then we take a short break and then we start again.
It's me? Oh, okay.
Yeah, so Carlo.
Okay. So this is actually a continuation. This is actually a continuation of the previous discussion. I'm also reacting to the beautiful provocation of by Pierre. And of course, I agree with everything that's been said in the answer. And my provocative answer is, Pierre, study a lot, which I know you do. But I think that's the right thing to do. We all did, in a sense. I want to say a couple of substantial things. I mean, of course, I completely agree with Chaslav. We have no reason whatsoever to believe that we're at the end of physics in fundamental physics. I mean, we're not at the end of science in chemistry and condensed matter by far, but by super far, even less in biology or whatever. But in fundamental physics, we have no reason. I see no reason whatsoever to believe we're at the end of physics. And I agree with Wayne, which is, I mean, there's never clarity in the moment of in the period of development. Even when historically it's, we would think, well, Maxwell had already written down the Maxwell equation, everything was clear. Then you look back, it wasn't clear at all. I mean, it's a total mess in a number of ways, and even you have to wait for after Einstein and the mathematical formula. So all that I agree. So in a sense, right, we are in the middle of the mess as usual. But I think it would be a mistake to neglect that there is something peculiar in the present time, which is not at all the first time that we are in this situation. We were historically, if you look at the last sort of four centuries, there have been other moments like that. And in fundamental physics, the peculiarity of this moment is it's the following. When I was a student at Bologna, I remember my lectures in particle physics. The point was, oh, there are all these hadron masses. Nobody has any idea where they come from. There are all this table of cross sections. Nobody has any idea where they come from. Okay, and if you read the discussion in the 20s, there are all these spectral values, and there's sort of this attempt of Bohr-Sommerfeld, but that they don't work. They don't give the right answer for helium. All this data that we cannot make sense of them. And there have been periods of physics in fundamental physics. There were mountains of data that we could not make sense of them. And then, remarkably, in various cases, I mean, QCD, bingo, incredible how put order in the hadron spectroscopy. Nobody talks about the hadron spectroscopy anymore because it's just chemistry out of QCD, and even the masses they compute them out of QCD. So it's a problem solved, so to say. And the atomic spectra problem solved. It's a Schrödinger equation. So, historically, I mean, there are people who do history much better than me here. I'm not talking science in general. I'm talking about what various time was considered fundamental physics in some sense, in various, even that, I suppose, evolved the notion of fundamental physics. But there were periods in which the community was submerged by unexplained phenomena and trying to make sense of them. And there were periods in which there weren't any unexplained phenomena. And we are in one of these periods in which there aren't any clearly unexplained phenomena. It could be that some of the phenomena we observe, we just are missing what they are. It could be. But give me a list of unexplained phenomena. It's it's incredibly short. I mean, we can disagree. Somebody thinks the neutrino masses, but we have a theory for neutrino masses. For cosmological constants, a theory for dark energy, and so on and so forth. Now, why I'm saying that? Because one reaction to that is, therefore, we cannot do fundamental science because we don't have because physics is it's out of data. Okay, it's just taking order out of data, and we're not like Kepler, who had all this Tycho Brahe data and working data, bingo, found the ellipses. We're not like Bohr that had all this Reidenberg formula, strange and bingo. So this would bring us to say, okay, there's no sense of trying to add something to fundamental physics. But we have a lot of examples, and that's the point, in which historically, in those situations, major steps were taken by carefully looking at the sort of streeting details and missing points in the successful theories. And we all know many, many examples of that. I mean, Einstein came out with general relativity essentially out of no data because, yeah, okay, Mercury, yeah, one number. The reason he could come out with general relativity is working very carefully on the contradiction between special relativity and Newton theory. Of course, he was trying to just make a relativistic theory of Newton theory like Maxwell did a relativistic theory of Coulomb theory. And Einstein himself, a few years later, 10 years before, came out of special relativity by just carefully looking at the reason of the successful Maxwell equations and trying to bring it together with the relativity of velocity, which he was convinced of both. So there is another strategy to get to novelty at the fundamental level, which is not built on data, but built on organized data, which are the current theories. We have current theories, these are organized data, and let's find that even Copernicus worked like that. Copernicus almost zero new data with spectral Ptolemy. He knew Ptolemy in the deep details, and if you look at Ptolemy in the deep details, there's something extraordinarily strange, which is the period of the epicycles of the difference of the internal planets is equal to the period of the epicycle of the external planet. All of them. So there's some very strange thing in the Ptolemaic model, which screams for interpretation, and of course you could painfully work it out, a very good one. So I'm not saying we know the fundamental physics, of course we don't, but I'm saying that in my opinion, this is my opinion, could be wrong. I mean, young people listen to the scientists and say, this sounds convincing, this sounds not convincing. In my opinion, fishing an idea out of the blue sky and looking for its consequences historically has never produced anything that I know in the development of science. Okay, saying, oh, why not? It could be that the world is like that. All right, so let's study the world like that. In my opinion, this is waste of intelligence. So historically, by looking at what has produced, novelty has been produced either by new data, the Tycho Brahe data, the spectroscopy, the hadrons, or by carefully looking at what is known, and within what is known, saying, good, there's something strident here to be matched, to be turned around and fix it better. There is a way to put the Maxwell equation together with velocity being relative. Yes, there is a way, incredible. Just get rid of simultaneity and it works. Okay? So it seems to me that for quantum gravity, we don't have the first strategy available, but we have the second strategy available. And in my opinion, and again, I'd be wrong, the third strategy, which is let's pull out of the blue sky ideas, I think, and this is a guess, is much less likely to be successful. Now, of course, there might be other hints that we might have, and the strangeness of quantum mechanics by itself could be one of those. So out of the strangeness of quantum mechanics, have something come out. I mean, this is a hint of something missing. So I'm certainly not saying that the contradiction between general relativity, the apparent contradiction between general relativity and quantum mechanics is the only hint we have. But I think we need hints and not ideas from the blue sky. Not say, okay, I have an idea. Why could be like that? Why not? But I spend my life studying that. That I think is a good recipe for failures.
So how?
I wanted to pick up a new theme, following up on a provocation that Laurent was bringing forward, I think, which is the role again of diffeomorphism symmetry in this whole discussion. And I'm much more familiar with the relativist side of this discussion, and so I wanted to frame the question by asking the quantum information crowd how they think about diffeomorphism symmetry, and if they think that there's an informational perspective on that symmetry that should be informing how we are trying to incorporate it into the theory, and whether they see that as already in place, or if they see places where that needs to be looked at in a different light.
Anybody wants to answer?
Actually, my earlier question about the potential interest in a bulky quantum theory is partly motivated by this question, because now I think from starting from purely from quantum theory, we have some understanding of how to think about symmetries and potentially quantum reference frames by means of looking at certain invariant algebras, relative algebras, etc. But this the way this formalism has been developed is just applies to, like, you take a Hilbert space and usually understood as, let's say, the Hilbert space at a given time, and applying these standard techniques. But if you would like to incorporate time, then it becomes very important how exactly you model, which kind of formalism you would use to describe evolution over space-time. No, not just evolution, but really quantum theory or quantum mechanics over space-time. And then if one would like to develop something analogous, it seems, at least to me, desirable if you have such a bulky space-time formalism, but that might come with certain modifications to the rules and certain adaptations. So it was just a question like that I was curious about. But then you're to address more specifically now this issue about diffeomorphisms. And this is also, maybe it comes a little bit with a question to the quantum gravity experts, is that I'm a little bit, let's say, maybe uneasy about the way these types of symmetries are implemented in the formalisms we discussed. For instance, I think if I understood correctly, Carlo, he said about composing regions that essentially composition does nothing. Did I correctly hear that? Am I correctly paraphrasing? But there is this, for instance, in your book, for example, there is this, you take a boundary region and something similar to the Wheeler-DeWitt equation, you conclude that actually it should not change under deformations because you would like that symmetry to be there. Now, on the other hand, it seems to me that there is another way of looking at these types of symmetries in classical theories. In classical theories, you have different types, an equivalence class of solutions that you could have this class of physical equivalent solutions. They look differently in the kinematic space, but you do not quite have this static feeling like a frozen universe that someone might want to interpret the Wheeler-DeWitt equation or a Hamiltonian constraint like. So one idea that, for instance, I've been thinking about is whether it might not be possible to try to incorporate this notion in a quantum theory by dealing with sets of equivalent quantum dynamics, or rather, if you'd like to keep all the gauge degrees of freedom, to have some theory of dynamics which is underdetermined, just like the Einstein equations are underdetermined when you carry these gauge degrees of freedom. And I do not think, when one imposes the constraints, it appears to me that one makes an assumption that may not be conceptually justified. And that is that you have a state, that you have a definite operator that you could write down, and then imposing, it has to respect the symmetries, it just arrives at a certain conclusion. But what justifies assuming that it even makes sense to say that you have a state, that you can write a state, or an operator, or observables, or whatever approach you take? Yeah, that's a kind of a question. I think that there might be alternative rules. And yesterday that was brought up also. We discussed briefly with Alex and Carlo about the origin of imposing first-class constraints. I mean, is that the only way that one can do that when going from classical to quantum theory? I think this is relevant because the will of the victim is that.
Okay, so there are two follow-up comments from Czaslaw and then Flaminia.
So thanks for this question. This is something which actually can bind these two communities. And so I think one of the main goals of the quantum reference frames were actually to go towards defining quantum diffeomorphisms and searching for the laws of physics that will be invariant under these extended symmetries. And there are a couple of papers already out. There's even one poster here that actually use this to solve some problems. And one of the ideas was that by changing the reference frame or quantum reference frame and assuming that Einstein's field equations have the same form in any of these choice of the quantum reference frames, you end up in the quantum reference frames in which the things appear simpler, and you solve this, and then you go back in whatever quantum reference frames you want. And here is an example. Let's say that you have a large mass put in a superposition, and now you want to be ignorant about how to solve a problem of a pro-particle falling into this superposition gravitational fields. You say, I don't know how to solve. I don't want to quantize anything in the first place. I'm ignorant about even whether I should quantize this. But then you say, but I believe that equations of motions will be the same even if I change to another quantum reference frame. And the one you would like to choose is, we call this to jump on the mass, because in this reference frame, the mass will be localized, but the pro-particle will be in the superposition. That's what quantum reference frames provide you in a very precise way. And then you are in the reference frame in which the metric is fixed, is definite, and at most it could be a problem of quantum field theory on a curved spacetime, and you know how to do it. And then you solve the dynamic of this, and you go back into the previous frame. And this turns out to be this symmetry, and that's maybe interesting, not maybe for this community that much, is that this symmetry is not obeyed by semi-classical gravity. It's not obeyed by any collapse model, but it's obeyed into one in which you add cats to your gravitational field source by the mass. Okay, we have worked this in very rudimental cases and simple cases, but I think that it's a promising way to go on, even, for example, in the quantum field version of that.
So Flaminia and then Al.
Should I go first?
Oh, and Lucian as well. Is it a comment, follow-up?
I thought.
Then Flaminia and then Lucian. Flaminia?
Okay, thanks. So yeah, I agree with Czaslaw that I also see this way of proceeding forward with the formalism quantum reference frames as a promising direction for the question that you have asked. And so maybe I just wanted to add something that is that, so the way we are proceeding with that is we take something that holds in general relativity, we take something that holds in quantum theory, we put them together, we take it to the extreme. So that is what we have been doing so far. So in particular, we are taking, for instance, a diffeomorphism transformation in general relativity. The principle of linear superposition in quantum theory, we put them together, we see what we get. And just to add on what Czaslaw has said, by assuming that the laws of physics hold in every quantum reference frame, we have also shown that you can generalize, for instance, the Einstein equivalence principle to quantum reference frames and to superpositions of spacetimes. And that's one that's one possibility. And then now the goal is to take this reasoning even further and see what we can say about more complicated situations and for more complicated scenarios in terms of space-time. And I would say we are still at the beginning of this research project, so we do not know exactly what is at the, I mean, we just had the first results, so it is now the time to apply this to more complicated situations. But I also think that this is a promising way of moving forward.
Okay. Lucian?
Yes, I've been thinking about this as well. One distinction between the work that I've been doing and Czaslaw and Flaminia and Catherine and other people here is this question of whether your frame is in some sense abstract, if it's like the coordinates in general relativity, or whether it's attached to a physical object. And like in general relativity, you can go the route of attaching a frame to a physical object, but it becomes problematic. So I've been trying to take the abstract approach and think of quantum coordinates, which are somehow analogous to the abstract coordinates of general relativity. And then that also suggests lots of generalization, or lots of analogies with GR. So in GR, you have a manifold, so the analogy would be something like a quantum manifold, which is covered by quantum coordinates. You have the covariant derivative, so maybe there is some analogy with that in the quantum case, and so on. The curvature, which curvature in GR measures the extent to which the second derivatives of the metric don't vanish. Maybe there is some object in the quantum case which is somehow analogous. So there is a suggested route to quantum gravity which is analogous to the route that Einstein took to general relativity. And it sort of builds on this idea of quantum reference frames, which Flaminia and Czaslaw have worked on, but takes it in this abstract direction. I'm kind of stuck in that project at the moment. Incidentally, I don't quite know how to take it forward, but at least the idea is there.
Another facet of my question that was implicit, but that I'd like to make explicit because I'd be very interested in people's thoughts. A big part of the history of diffeomorphism symmetry is a confusion about what's redundancy and what's symmetry. And I see that confusion recapitulating itself in discussions of diffeomorphism symmetry sort of repeatedly. In the spirit of Pierre's question, I'd love to have an informational perspective that helps me to sort out the question, that's redundancy and that's not. And to face that in a very clear, precise way. And it seems information might have the potential to do that, to sort of say, oh, this is redundancy and this is information carrying. So if you have comments on that, I'd be interested.
Maybe I can try to address it a little bit. Sort of another, in this quantum reference framework, often it's phrased as a communication protocol. So like I would want to communicate to you maybe up in Z or something like this. But if we don't share a common reference frame, then I just send you up in Z, you would have to average over all possible orientations, average over SO3. And I couldn't send you any information, right? So often what we think of is appending a second system as a quantum reference frame. And in that case, there's certain properties of how it transforms under the group, namely if it transforms asymmetrically under the group, then it serves as a good reference frame and you can talk about big classical limits. And then when you do this average, there's still some quantum information I can send to you as a communication protocol. But now you ask about diffeomorphism, and what, I mean, when I look at the literature, what I see is that a lot of the quantum information literature has focused on compact Lie groups, right? And they have a nice normalized R measure that you can do a good averaging over. But when you go to the diffeo group, right, some of this structure is gone. So I think there's kind of like a concrete mathematical question of how to generalize some of the quantum information protocols to the diffeo group. So I don't know, maybe that's a concrete way where you can get rid of sort of background information that's appealing to a background reference frame by doing these averaging processes. And then it's difficult to average over the diffio group. So just leave it at that.
Thank you. I have a different question. So this is actually challenging the local holography program. So we have learned a lot about this operational way of thinking from the quantum foundation community on how we gain knowledge from the nature. So I want to ask people who work on local holography is, so this is not like tabletop experiment, but at the thought experimental level, are there some operational way we can justify or test the local holography to say that this is a more efficient way of organizing the data quantum gravity information? And also, then a related question that would be for quantum foundation community is, what are the shortage or not a sufficient aspect of this operational approach in terms of understanding the nature? Thank you.
So any follow-up, direct follow-up? Okay, then Eugenio.
And also a new question. Yeah, so this is a question about the general boundary as a formalism and how can it help us asking questions if we wouldn't be able to ask easily the formalism. And in particular, I'm referring to a figure that appeared in Adamantia's presentation and also in Carlos' presentation. This one of the black to white tall transition and the fact that the general boundary can help there phrase questions sharply. And that was beautifully presented in one of the figures of Adamantia. So the question I want to ask is, the current version of the general boundary that I understand seems to me to be a generalization of the S-matrix formalism used in a particle physics, for instance, but to finite regions. What I mean is a specific class of in-states and out-states, but for this boundary for finite regions. So this is this has played an important role in quantum gravity, it's playing an important role, but it's a selection of a class of in-states and out-states. So we have seen and we have asked more than once in the past few days about superpositions of spacetimes and ways to probe the effect of superpositions of spacetimes. And in a situation like this one where there's formation of a black hole and transition to a white hole, I think many of us expect that you can think of it as you give initial conditions, you evolve them, and in the end you're going to have a superpositions of spacetimes with a certain probability of a transition to a white hole. Do you see a way of asking this kind of questions within the current version of the general boundary formalism, or do we need some more flexible version where we have states that don't belong to this class of general boundary states?
So if somebody wants to answer, then we get the answer. Yeah.
Okay. So indeed, the general boundary formulation was inspired by the S-matrix approach. Sorry? Here? Okay. Yeah. Okay. So I said that indeed the general boundary formulation was inspired by the S-matrix approach in quantum field theory. And there is this abstract generalization in closed boundaries. To my knowledge, I don't know an example of completely closed application of, but I showed an example on of quantum field theory in a closed region on the hypercylinder. So this region is bounded by time-like surfaces. And in this way, you can use, you can generalize where instead of using spatial hypersurfaces, you can use you can generalize the formalism to time-like hypersurfaces to have states there defined, and this involves also a generalization of the notion of the Hilbert space, because you need to define more. Okay, you don't have the positive and negative modes that you have when you have the space-like hyperspaces. So you instead of somehow you generalize this framework, and the new modes appear, which are called evanescent, and they are more related to these. Okay, in the solutions of the differential equations on these time-like hypersurfaces. So that's one answer. Probably, I hope it is. Okay, so I don't know about the black hole example. So this example is actually is a finite dimensional example. So it's you can formulate it like so. The way it was formulated was that you ask time of arrival type of question. Is the time, will I find the time to be in the time interval T1 till T2 while I run, let's say, this operation? First, you formulate the theory, the classical theory in this way, and the way it is actually calculated is by considering coherent states on this hypersurface that separates the quantum and the classical region. Yeah.
Okay, so we got an extensive answer to the question, I hope, and then we make an exception to the rule, which is that we have a follow-up to the previous question. Yeah.
Okay, so shortly, I wanted to answer Ling Chin's question. So I will interpret operationalism in a loose sense in terms of what can we observe. And in this sense, I would say that practically our limitation is what experiments can do. But in principle, also our imagination, our intuition only gets as far as as what we can, like the concepts that we now have solid in our understanding now, and to push them. And after we have pushed them far enough, then if we don't have experimental data, there's a limit there. And there, I think that this community can help in the interactions between the different parts of the community can boost this further and put methods and tools together to proceed.
Very good. Follow-up? Yep. Brief follow-up?
Yeah, this was also a follow-up to Ling Chin's question about the kind of maybe limitations of operationalism. Yes, I think we use the operational approaches quite a lot in quantum foundations. There's lots of things I feel which aren't adequately described. If I write down the wave function of the universe, like operation, I can't make sense of that because we describe states relative to measuring devices. And yeah, if you look specifically at operationalism as we use it, it's in terms of prepare, measure, and transformation devices with probabilities. So yes, you need to do like large runs, collect lots of statistics. many physical phenomena aren't like this, right? Like, I don't like, prepare a star in lots of different positions and then transform it and measure it. So yeah, I think there's kind of, it's very useful, but it has severe drawbacks in these senses. So yeah, I think it's maybe important to move beyond it for these types of questions.
An even briefer follow-up.
I don't feel that this doesn't completely fit in. Of course, you cannot prepare, or maybe not yet, and you cannot transform, maybe not yet, but you can measure. I mean, when you say the observations, we want to explain whatever, the sun, or the color of the sun, or whatever. I mean, we do perform then at the end measurements. It's just that we are already in domain when we make very coarse-grained measurements, such that we basically can do it within the classical physics. So I don't think that we ever go beyond this paradigm. But nevertheless, I want to confess that from my own experience, I saw a shortage of the operational approach. And this is about the notion of redundancy that I never appreciate enough. Because why should you have a redundancy in the description if you don't see these redundancies? But then when you look, and that's what I learned from Carlos' paper and you guys, once you start to interact with the things, then you see that this redundancy actually can come up as an observational effect. But because you were looking at the subsystem, you didn't care about that. And then that's what you would miss on the next step when you talk about interactions, one operational element. So that tells me that one should be open, one should stick at the end of the road, what Flamini also said on the operational approach, but you should be a little bit more open for some elements that do not have a direct operational meaning. Yeah.
Okay, so we have also two questions which are somehow stuck on the podium, but they are rather specific technical questions on spin forms, spin networks. So I would encourage whoever asks them to just go to any of the experts in the room and ask afterwards. And then we have another point stuck here, and I've seen it before. It was already in some of the previous sessions, and I suspect it's actually been put here by the organizers. So it says, this is a fantastic conference, and we have to thank the organizers.
Yes. So just a few informations regarding the trip of tomorrow.
So tomorrow we're spending the day at the Pinery, which